Hey guys, welcome back. Today I'm going to teach you how to multiply and divide radicals. Once we get to the pattern, it's actually pretty simple, but instead of just showing you how to do it, I'm going to try to help you remember the properties of exponents, because the properties of radicals are the properties of exponents, because radicals are exponents. So let's see if we can remember how to do this stuff here. So if I have a plus b and I'm squaring it, so a plus b squared, anything we're squaring is like multiplying it by itself. So that would be a plus b times a plus b. And then on this one, we would actually have to distribute the a through to both terms and then the b through to both of them as well. And when we do that, it's going to actually be FOIL, if you remember what that stands for. So first, outside, inside, last. So a times a would be the first. The outside is a times b, which is just AB, and then the inside is BA, which is the same thing as AB, and then the last is B times B, which is B squared. So all that together would be A squared plus 2AB plus B squared. Alright, so the reason that this ended up happening this way is because the exponent was being distributed through addition instead of multiplication. If it was being distributed through multiplication, it's a whole lot easier. So for instance, a times b squared is just going to be ab times ab. Now since all these are the same level of multiplication, it's just a times b times a times b, then you can rearrange this with the commutative property of multiplication to leave it with a squared times b squared. So in other words, we just have ab squared is the same thing as a squared b squared, which essentially meant that we were just able to distribute through the exponent through to both of the terms. Now it's not that simple when we're separated by addition, but when we're separated by multiplication, it works out really, really well, because exponents really are just repeated multiplication. Alright, so if we can distribute exponents through multiplication, we can also reverse distribute, which is the same thing as factoring them out. So in this case, if we have 3 times 2 and we're squaring that, we can distribute the exponent through to both those terms. So that's the same thing as 3 squared times 2 squared. And let's see if that actually works. So what is that? 3 times 2 is 6 squared, and 6 squared is 36, right? And this is going to be 9 times 4, which is also equal to 36. So yes, it works. Let's try it over here. So what we just did is we just distributed the exponent through multiplication. Let's try to factor it out. So basically I'm going to factor out the square into both of these. So 2 squared times 4 squared is equal to 2 times 4 squared. Let's see if that works. So 2 squared is 4. 4 times, I don't know why I'm doing it here. Anyway, 4 times 16, and 4 times 16 is going to be 64. Over here, we factored it out, so 2 times 4 is 8. 8 squared is 64. So it does work. We can distribute and we can also factor out exponents as long as we're dealing with multiplication. Now when we're dealing with addition, it's FOIL and it's different. It's not going to work. Well, if this works for squaring, it also works for the square root, because the square root's just another exponent. It's just an exponent, which is the half power, which would be a proper fraction or something. So I can distribute through the half, basically distribute through the square root through both of these, just like I did up on top. So that would be really the square root of 3 times the square root of 2. And if I can take it out, I can also put it back in. So in other words, this is like one big radical, because it's the square root of 3 times 2, which is the same thing as the square root of 3 times the square root of 2. So if you're multiplying any two radicals, basically you just combine the parts that are under the radical and multiply them together. So real simple. But it only works if they're on the inside of the radical. So let's look at an example. So 3 times 2, or rad 3 times rad 2, is going to be rad 6, right? Or rad 3 times 2, which is rad equals 6. Now 2 times rad 3 times rad 2, basically you're going to multiply the parts on the inside of the radical, but the part on the outside staying on the outside. So this is just going to be 2 rad 6, or 2 times rad 3 times 2. Now if we have two parts that are in front, we multiply the parts in front of the radical. So in other words, that's going to be 3 times 2. And then we multiply the parts in the radical, which would be 3 times 6, which would give us radical 18. So altogether, this is going to be, see, on the outside we have 6, so 6 radical 18, or 3 times 2 radical 3 times 6. So the parts on the outside of the radical stay on the outside, part on the inside of the rad stay on the inside. That's really the pattern that you need to know for multiplying radicals. Now the only difference is with radical 18 is that we can break it down and simplify it, because it has a factor of a perfect square of 9. So anyway, just breaking this down, we already have the 3 times 6, right? You could have done 18, but then you just break it right back down. 3 and 6 is going to be 3 and 2. Then if you notice, we have 2 3s, so the 2 3s can come out to join these. So that's 6 times 3, which would be 18. and then left on the inside is the 2 all by itself. So it would be 18 radical 2 would be our final answer. All right, so let me show you the trick for multiplying radicals. So when we have two radicals we're multiplying, anything that's on the outside of the radical, the coefficient, is going to stay on the outside. So that's going to be 3 times 2, which is going to be 6. It's still on the outside of the radical. Anything on the inside is going to stay on the inside unless we have multiple factors that can come out. So I'm going to go ahead and, it's basically going to be 6 times the radical 15 times 6. Now the 15 and 6, I can actually break those down to get 5 and 3, and then 3 and 2. And when we do that, we notice that we have a common 3 that can come out to join the other 3 and the 2, which make the 6. So that's going to leave us with 6 times this new 3 that we took out, and then on the inside 5 and 2, which is 10. So 6 times 3, which is 18, radical 10. And the 10 can't be broken down anymore because remember, it's just that 5 and the 2. So it can't be broken down anymore. So we're good. All right, let's do another example of this. So negative 5 and 2. So on the outside, we're going to have negative 10. On the inside, we have 10, which can be broken. Well, 10 and 10 and 15, which is 150. You could multiply them together, but then you're going to have to break them down right back to the 10 and the 15. So let's just break them down now and see if anything comes out. So that's going to be 2 times 5, and then 5 times 3. And on this one, we notice the 5s will come out to join the negative 5 and the 2, which gives us negative 10 times 5, which is going to be negative 50. Oops. Yeah, there's something wrong with that. Close your eyes. Okay. And then left on the inside is 2 and 3, which would give us 6. So radical 6. So altogether we have negative 50 radical 6. All right. Okay, so that's a trick for multiplying radicals. Now let's look at division. So with division, we have this reverse distribution of exponents, not across multiplication anymore, but now it's across division. Because multiplication and division are kind of on the same level playing field when it comes to the order of operations. Pretty much anything we can do with multiplication, we can also do with division. So what I'm saying is that we can actually distribute through the exponent across the numerator and denominator, just like we were able to distribute through cross multiplication. It's kind of cool. So in other words, like if this is 10 over 5, that's really 1/2, right? And 1/2 squared is 4. Well, what is 100 divided by 25? Well, that's also 4. So cool, it actually works out. Let's see if we can go the other way, right? So 2 squared would be 4. 4 over 16 is going to be 1/4. And over here, this is 1/2 squared, and half of 1/2 is also 1/4. So it actually works out, which is kind of nice. So yeah, let's see how that actually plays out with radicals. So if I have radical 16 over radical 8, these radicals are like 1/2 power, and I can basically factor those out to put them under one big radical. So basically I factored out the 1/2, the exponent, through both of these. So I pulled it out just like I did up here. All right, now that they're under the same radical, that's like having one giant radical. So if we have two separate radicals in a numerator and denominator, we can kind of imagine that they're under the same radical. And now that we have that, this 16 and the 8 can be reduced. And so that's actually going to be 2, right? So big radical, 2 over 1, which is just 2. Which then can be broken back by distributing it through, like we did over here, to give us the radical 2 over radical 1, which radical 1 is the same thing as 1, which leaves us with just simply radical 2. So, long story short, what I'm trying to say is that anytime you see anything that's in a radical, like here, if you see a fraction that can be reduced, just like this, like 2 over 1, remember it's still going to be in the radical, but that's pretty much what we're going to do. So that would give us the answer of radical 2. All right, so let's use that and practice dividing radicals. So I got rad 6 over rad 2. Both of these are already in the radical, so I can go ahead and reduce them. What I'm actually doing is factoring out the radical and then putting the radical back in. But basically, if you see this, they're both in the radical, and I can reduce 6/2, which is 3 over 1, right? Just remember, it's still in the radical. So that'll give me radical 3 over radical 1. Radical 1 is the same thing as 1, so it's really radical 3 over 1, which is radical 3. All right, so what happens if you have anything on the outside? Well, just like with multiplication, stuff on the outside stays on the outside, and the stuff in the radical stays in the radical. So we're going to do this in 2 parts. So the part on the outside, we're going to reduce that as its separate fraction. So 9/3 is the same thing as 1 or 3 over 1, and then reduce the parts that's in the radical, which is going to be 4 over 1. So basically we're going to have 9 radical 4 over 1 radical 1. 1 radical 1 is the same thing as 1. So we basically just have 3 radical 4. And if you don't like seeing radical 4, that's because that actually can be reduced and the 2 can be taken out. So altogether this is going to be equal to 6. The last thing I need to teach you is how to rationalize the denominator. So with fractions and radicals, we actually don't want to have a radical in the denominator. It's just considered an improper form. So we want to do something called rationalize it because it's an irrational number. We don't want to have irrational numbers, which are numbers that just keep repeating over and over again. That can't be written as a fraction, in other words. We don't want to keep those in the denominator. So how do we get rid of the radical in the bottom and the denominator? Well, what we're going to do is we're going to multiply the denominator by radical 2. And when I do that, rad 2 times rad 2 is just going to be a regular 2. But if I multiply the denominator by radical 2, in order to keep this same, I have to multiply the numerator by radical 2 as well. It's the same thing as like subtracting the same thing for both sides, multiplying both sides by the same thing. It's the only way we can keep it balanced. The other thing is that radical 2 divided by radical 2 is 1, and if we multiply anything by 1, it remains unchanged, right? Because it's a multiplicative identity. So 3 times radical 2 is just going to be 3 radical 2, and then rad 2 times rad 2 is just a regular 2. So you probably notice some patterns whenever we're rationalizing denominators, but that's a process that we're going to do. All right, so let's look at another one. If you notice on this one, the 4 and the 2 that are on the outside or in front of the radicals, those can be reduced. So I'm going to go ahead and reduce that as a separate fraction, and I'm going to reduce the part in the fraction as well. So in the front, 2 over 4 is just going to be, or sorry, 4 over 2 is just going to be 2 over 1. And then inside the radical, this will save me time in the long run, by the way. 4 over 6 is the same thing as 2/3. So that's rad 2 over rad 3. Now, when I got done, I still have a radical in the denominator. It's not radical 1, so it's not like it just goes away. So I have to multiply by rad 3 to get rid of it, which will make it a regular 3. And then up here, I have to multiply the same thing by radical 3, otherwise it won't be balanced. We'll be multiplying by something that's not 1, and we change the fraction. So that's going to give me 2. In the front, we have 2, and then radical 6. So I have 2 radical 6 over 3. Now, I can look again over here to see this 2/3 because they're still in front of the radicals and see if those will reduce, but they don't. So I'm done at this point. This is the most reduced form that I have. All right, so let's go ahead and start the assignment, not doing too bad on time. So we want to multiply the radicals. So basically we're going to put them together. It's the same thing as radical 12, and you could do it that way where you have radical 12. In fact, I'll show you like that. So rad 12, but then once we get to radical 12, we're going to have to break it down again, which is right back where we started with 6 and 2. So it's a lot easier just to break them down at the beginning and then see what can come out together. So when I have this, I have 6, which is going to be 3 and 2, and I have a 2 over here. So what's going to come out? Well, I got a common pairs of 2's. So in the front, outside the radical, we're going to have 2, and the left on the inside is radical 3. So it'll be 2 rad 3. Same thing you would get if you multiply rad 6 times rad 2, rad 12, break it down again, and then here we would have 2 and 3, so the 2's can come out in the front, and then left on the inside is the 3. So same thing. All right, multiply. You could multiply those together to get a radical 100. In fact, I'll do that real quick. So when we have radical 100, 100 would be broken down as 10 and 10, right? So the 10's come out, and that's just going to be equal to 10. And the square root of 100 is 10, by the way. So let's do this the other way. Go ahead, and 5 is a prime number, so it won't be broken down. 20 can be written as 5 times 4, and 4 is 2 times 2. So you'll notice a pair of 2's come out and a pair of 5's. So altogether, that's going to be 10, right? 5 times 2 is 10. So pretty good. All right, number 5. You can multiply them again if you want to. And if I do that, I'll get radical 150. And then, but the problem is I'm going to end up breaking it down right back where I started with the 15 and the 10. So you might as well just break it down over here, okay? So 15 is 3 times 5. 10 is 5 times 2. And notice we have a common pair of 5's that can come out of the radical, and then left on the inside we have the 3 and the 2. So that's going to give me 5 radical 6, because the 3 times the 2 would be multiplied back together again. You get the same thing if you did it over here, again, just trying to save you a step. All right, 7 and 9. Now we're multiplying radicals with their coefficients. So it's pretty simple. Just multiply the coefficients first and keep them separate in front of the radical, and keep your stuff in the radical in the radical. So 5 times negative 2 is going to be negative 10, so that goes on the front. And then 2 times 3 is going to be radical 6. Now I know these are already broken down because they're prime, and so those radicals cannot be reduced. So we're done at that point. Same thing over here. I'm going to do 3 times 5, which is going to be 15 and the new, in front of the radical. And then here, if I have 6 and 6, now you could do that as radical 36, but then you notice the 6's both come out, right? So there's a pair of matching 6's, so I'm going to have 15 times 6, which is going to be 90, I believe. Yeah, so that should be your answer. It should be on the answer bank. All right, now 15, we want to rationalize this denominator. So anytime you see a radical in the denominator, we have to rationalize it. So I'm going to get rid of a radical 2 by multiplying by radical 2. And that's going to make it a regular 2. But if I multiply the denominator by rad 2, I got to do the same thing to the numerator. So that's going to be 4 times rad 2, which is just 4 rad 2. Ooh, but then if you notice these parts, that's why when they're both blue, it's kind of nice. But those can be reduced, right? So because they're both the constants in front of the radicals, they're not under the radicals, so we can reduce them. So 4 halves is going to be 2, so this is just going to be 2 radical 3. All right, so I'm going to reduce, before I do anything else, I'm going to reduce the parts that are in front of the radicals, and then I'm going to reduce the part here if I can. Well, 3 halves won't reduce, but 2/4 will. That's going to be 1 half. So in the front, I have so just 1 radical 3 and then 2 radical 2 on the bottom. So that basically reduced to 1 half. Then this is not rationalized, right? I can't have this radical in the denominator, so multiply it by radical 2. If I do it on the bottom, I got to do the same thing on the top. So radical 3 times rad 2 is rad 6, no big deal. And then here, 2 radical 2 times radical 2, we multiply the parts in the front, which is going to be 2, and then parts on the inside, which would be radical 4, which of course the 2's come out, and that's the whole point of multiplying it by itself. It's like squaring it, in other words. Let me show you that. So radical 2 times radical 2 is really radical squared, and that's really like that's like 2 to the 1 half times 2, which is really just 2 to the 1 power, which is 2, right? Okay, so anytime you multiply a rad 2 times itself, it's like you're squaring it, and then it pretty much goes away. Or in other words, this is the same thing as radical 2 times radical 2, which is radical 4, and radical 4 has 2 2's in it, and the 2's come out, right? That's the whole point of what we're doing here. All right, so here we have 2 times 2, which is going to be 4. Now the 6 and the 4 cannot be reduced because one's in a radical and the other's not. So this is really like it's out in the front, and this is over like on the side there. So the understood part here would be like 1 radical 6 and then 4 radical 1. And so you notice these parts really 6 over 1, and that part is 1 over 4. But it's actually just being shown that way. All right, let's do 2 more together. Again, I want to reduce the parts in the front, so the coefficients, that's just going to be 2 over 1, and then also reduce the parts that are inside the radical. So I can pull a 5 out here, which is going to be 5 over radical 2. So I'm going to have 2 radical 5 over 1 radical 2, okay, which is just rad 2. Rationalize the denominator, multiply both the top and the bottom by rad 2, which will give me a regular 2 on the bottom, and then 2 radical 10 on the top. Now these 2's can be reduced, and so that's going to leave me with just simply radical 10. 21. There's nothing that can be reduced with the coefficient, so I'm just going to keep it there. However, the 4 and the 12 can be reduced, so I'll take a 4 out. So that's going to give me radical 1 on the top, which is just 2 rad 1, which is the same thing as just 2. And then on the denominator, we're going to have radical 3. To rationalize the denominator, multiply the numerator and denominator by radical 3, which will leave me with 3 on the bottom, and then 2 rad 3 on the numerator. Now these 3's cannot be reduced because they're not both under the radical, and the 2/3 is already reduced, so we're good to go. All right, so that's all that I have for you today. Let me know if you have any questions. So we've reduced radicals, we've add, subtract radicals, just like combining like terms, and now we learned the trick to multiplying and dividing radicals, or reducing them, essentially just to keep the stuff in front of the radical, and the stuff in the radical, and then at the very end, see if you can reduce. And then also, don't forget, you need to rationalize denominators. That way your answers will match. So if you forget to rationalize the denominator, your answers won't match the answer bank. So please remember to do that. And then we'll be ready for the Pythagorean theorem tomorrow. And then hopefully whenever we come back in person, we'll try to do our game. But we'll see. I have no idea when that'll be. But I'll see you guys around. Let me know if you have any questions.